Am I audible? I'm sharing my screen, okay? Network. I have some network issues.
Shear and moment in beams. When a properly supported beam is subjected to loads, it is going to deflect. Although
So,
such a
starting
deflection
from
is
the
not
previous
visible,
video,
it does cause internal forces
let
to
me know if
develop in the
the
metal.
screen is not
Take
visible.
segment
Okay?
AB of this simply supported beam. Under the applied load, the segment deflects downward.
Continuing
This
with the last video.
deflection compresses the top part of the segment while stretching its bottom part. We say the top part is in compression and the bottom part is in tension. Imagine the beam consists of an infinite number of long fibers. All the fibers along the top part of the segment are in compression, although to a different degree, and the fibers along the bottom part are in tension. The fiber that lies between the top and the bottom group, however, is neither in compression nor in tension. I have shown that fiber in color green. Suppose we straightened the fibers without changing their new lengths. Then we can see that the top fiber is the shortest and the bottom fiber is the longest in the section. And of course, the middle fiber experiences no change in its length. We refer to the axis that passes through that middle fiber as neutral axis. The topmost fiber, since it is the shortest, can be viewed as having the largest compressive force acting on it, and the bottom fiber, since it is the longest, then must be subjected to the largest tensile force. The force acting on each of the remaining fibers varies based on its position relative to the top and bottom fibers. It is important to note that the fiber along the neutral axis carries no force. Here are the forces present at the two ends of the segment. From the direction of the forces, it should be obvious that they want to cause a rotation. These forces want to turn the right vertical plane in the counterclockwise direction, and these forces want to turn the left vertical plane in the clockwise direction. We can argue that this rotational tendency is being caused by an internal force, which we call a bending moment. Let's refer to this compression force as P1 and denote its distance from the neutral axis as D1. We can do the same for the other forces. So, associated with each force is a corresponding distance from the neutral axis. The bending moment is defined as the sum of the product of each force and its distance from the neutral axis. So we have a clockwise bending moment at the left end of the beam segment and the counterclockwise moment at the right end of the segment. This pair is referred to as a positive bending moment, since they associated with compression along the top fiber and tension along the bottom fiber in the segment. A negative pair of bending moments acts in reverse. It causes tension along the top and compression along the bottom fiber of the segment. Now that we have a better understanding of the nature of bending moment in beams, let's see how we can calculate it. Consider a simply supported beam subjected to the weight of a person. Assuming he is standing at the midpoint of the beam, we wish to determine bending moment in the beam 1 meter away from the right support, at point C. We start by determining the beam's support reactions. Here is the free body diagram showing 3 unknown forces. There are 2 reaction forces at the pin and 1 reaction force at the roller. We write 3 equilibrium equations, then solve them for the unknowns. Having determined the reaction forces, we are now in the position to calculate bending moment at C. To do so, we cut the beam at C, separating it into a left segment and a right segment. This exposes the internal bending moment at C. The moment appears in both segments. The one for the right segment is drawn in the clockwise direction, and the one for the left segment is shown in the counterclockwise direction. Note that each of these internal moments tends to compress the top part of the beam near the cut point. Hence, it is considered to be acting in the positive direction. We can calculate this unknown bending moment using either the left or the right segment of the beam. To determine the moment, we simply apply the moment equilibrium equation to point C. For the left segment, the equation is, solving it for mc, we get bending moment has a unit of force times length. So here we have the moment expressed in kilonewton meters. Of course, we could have calculated the moment using the right segment of the beam, which would have given us the same value for mc. Let's calculate bending moment at another point, say point D. We start by cutting the beam at D. Draw the free body diagram for either the left or the right segment of the beam. Then write and solve the moment equilibrium equation in order to determine the internal moment. In addition to bending moment, beams carry another internal force. We call it the shear force. It is a force parallel to the cross-section of the beam. To see why shear develops in a typical beam, consider segment CD. It is subjected to distinct moments at its left and right ends. This pair of moments causes compression in the top fibers and tension in the bottom fibers of the segment. Let's show the compression and tension forces acting on the fibers this way. Since the left end moment is larger than the right end moment, compression and tension forces at the left end are going to be larger than their counterparts at the right end. I'm going to refer to the total compressive force at the left side as Q, and use R for the total compressive force at the right side. So Q is greater than R. Also, let's use M and N for the total tensile force at the left and the right sides, respectively. Then M is greater than N. Suppose we separate the tension zone from the compression zone, like this. This separation exposes another internal force in the segment, a horizontal force that acts in between the two segments. Why does such a force exist? To maintain static equilibrium. Since Q is greater than R, then another horizontal force needs to be present for the sum of the forces in the x direction to vanish. We call this a shear force. Also, notice how H wants to rotate the top segment in the clockwise direction. The shear force causes a clockwise moment about the horizontal axis defined by Q and R. The same happens in the bottom segment. H wants to turn the segment clockwise about the axis, shown using dashed line. To prevent the rotation of the top segment, a pair of vertical forces causing a counterclockwise rotation needs to be present. These are also shear forces since they act parallel to the cross-section of the beam. I'm going to refer to this shear force as VT. We get a similar pair of shear forces in the bottom segment as well. Let's refer to them as VB. Then the total shear force at the left and right end of the segment is the sum of VT and VB. This shear force comes about because of the differential bending moment at its ends. We can easily determine the shear force by writing and solving the moment equilibrium equation like this. So at point D, the internal forces in the beam are, note how these forces ensure that both the left and the right segments of the beam remain in static equilibrium. The sum of the forces in the y direction and the sum of the moments in both free body diagrams equal to 0. This makes calculating shear and moment in beams rather straightforward. We don't need to figure out the internal tension and compression forces in the beam in order to determine shear and moment. We can determine these forces directly from the static equilibrium equations. Consider a statically determinant beam subjected to two concentrated loads, like this. Let's calculate the shear and moment forces at the midpoint of the beam. We always start by determining the beam's support reactions. Here is the free body diagram of the entire beam, and here are the three equilibrium equations. Solving them for the unknown reactions, we get Now let's cut the beam at its midpoint, exposing the internal shear and moment at the point. Note that I am showing the moment in the positive direction here. Shear is considered positive if it wants to turn the beam segment in the clockwise direction. This means a positive shear shows up as a downward force at the left end of the cut, wanting to turn the left segment of the beam in the clockwise direction. The shear force at the right end of the cut then needs to be placed in the upward direction, again, wanting to turn the right segment in the clockwise direction. So, by convention, any time we cut a beam, we draw a pair of bending moments and a pair of shear forces. The shear force at the left end should be downward, and the one at the right end should be upward. The moment at the left end should be in the counterclockwise direction, and the one at the right end should be shown in a clockwise direction. Obviously, we can use a different sign convention here, but regardless of the sign convention being used, it is imperative to keep in mind that the internal forces at the left and the right ends of the cut must cancel each other out. So the two shear forces must act in opposite directions, and the two moments must act in opposite directions so that their sum ends up to be 0. Let's use the left segment to calculate V and M. Here are the two equilibrium equations. Solving them for the unknowns, we get We will continue this discussion in a future lecture. For now, see if you can solve the following problems.
I'm sharing the next screen, okay?
Shear and moment equations. In the previous lectures, we talked about shear and bending moment in beams and how to calculate them at specific points. For example, given this beam, we can determine shear and moment at C by first determining the support reactions and then by cutting the beam at C and writing and
Is it
solving the
visible?
equilibrium equations for segment AC. Since shear and bending moment may not be constant along the length of the beam, we need to be able to either express them mathematically or graphically
Okay.
so that their maximum and minimum values can be readily determined. In this lecture, we focus on the mathematical shear and moment equations. In the previous lectures, we talked about shear and bending moment in beams and how to calculate them at specific points. For example, given this beam, we can determine shear and moment at C by first determining the support reactions and then by cutting the beam at C and writing and solving the equilibrium equations for segment AC. Since shear and bending moment may not be constant along the length of the beam, we need to be able to either express them mathematically or graphically so that their maximum and minimum values can be readily determined. In this lecture, we focus on the mathematical representation of shear and moment in beams. Once we have the necessary equations, we can then graph them in order to visualize how shear and moment change along the length of the beam, and more importantly, to locate the points at which these internal forces attain their maximum and minimum values. Consider this steel and glass building, designed and constructed to serve as an art center. Let's highlight 3 specific beams in the skeleton of the structure, each subjected to a different loading case. We are going to show how to write the shear and moment equations for each beam. We use the beam on the second floor to formulate the shear and moment equations due to concentrated loads only. For the short beam on the first floor, we end up writing the shear and moment equations due to a uniformly distributed load. And the beam on the side of the building covers the case of a partially distributed load combined with a concentrated load. In this presentation, we are going to assume that all 3 beams are simply supported. Let's start with the long beam on the second floor. Suppose the concrete roof panel, shown in green, is supported by 2 transversal beams only. This means that the weight of the panel is going to be distributed to the 2 beams. Assuming that the specific weight of concrete is 24 kilonewtons per cubic meter, the roof thickness is 229 millimeters, the length of the red beam is 10 meters, and each of the 2 transversal beams has a length of 3.5 meters, then the uniformly distributed load on each beam is going to have a magnitude of 27.48 kilonewtons per meter. The distributed load magnitude is the product of the specific weight of concrete, the thickness of the roof panel, and half the length of the long beam. If we multiply the magnitude of each distributed load by the length of the transversal beam, we get the total load per beam. If we divide the total load by 2, we get the magnitude of the concentrated load that is being exerted on the red beam, which is equal to 48 kilonewtons. Assuming that the beam is simply supported, we are now ready to analyze it and write its shear and moment equations. First, we need to calculate the support reactions. The free body diagram for the beam embodies 3 unknown reaction forces. Using the static equilibrium equations, we can determine the unknown forces. They are AX equals 0 and AY equals BY equals 48 kilonewtons. Note that the 2 applied loads divide the beam into 3 segments. This means that we need to write 3 shear equations and 3 bending moment equations, a pair of equations for each segment. Imagine that the x-axis runs along the length of the member with the origin of the coordinate system being located at the left end of the beam. So our equations are going to be written in terms of x. For each segment, we are going to cut the beam at some distance x from the origin, draw the relevant free body diagram, and then write the equilibrium equations so that we can express shear and moment in terms of x. For the left segment, we cut the beam at an arbitrary point between 0 and 2.5 meters. We label the distance from the left end of the segment, the origin, to the cut point as x, where x is defined between 0 and 2.5 only. At the cut point, we draw a shear force and a bending moment. These are drawn in the positive sense, meaning shear is acting downward and bending moment is acting in the counterclockwise direction. This notation is consistent with our sign convention, according to which a positive shear tends to rotate the beam segment in the clockwise direction, and a positive moment causes a concave up deformation. Now we write the two equilibrium equations. The algebraic sum of the forces in the y direction must be 0, and the sum of the bending moments about point A must be 0. Solving these equations for V and M, we get. Note that in this case, shear is constant throughout the entire segment. Shear is not a function of x. Bending moment, on the other hand, does vary with x. Now that we have the shear and moment equations for the left segment of the beam, we are ready to write a similar set of equations for the beam's middle segment. Cut the beam at some arbitrary distance from the origin and label the length of the segment x. Here too, we are going to show shear and moment at the cut point as V and M. We can get the shear and moment equations for the segment by writing the equilibrium equations and solving them for V and M like this. This pair of equations tells us that throughout the middle segment of the beam, shear is 0, while bending moment remains constant. Finally, to write the shear and moment equations for the right segment of the beam, we cut the beam at some distance x from the origin, where x is between 7.5 and 10. Then we write the equilibrium equations and solve them for V and M. Here are the shear and moment equations for the right segment of the beam. In summary, given that the concentrated loads divide the beam into 3 segments, we must express shear and bending moment in a piecewise manner using 3 equations. Note that for each bending moment equation, the interval within which x is defined contains its boundary values. For example, the first bending moment equation is valid for any x value between 0 and 2.5, including at 0 and 2.5. However, the first shear equation is valid only for x values greater than 0 and less than 2.5. Why? Because shear cannot be defined at the point of application of a concentrated load. So for the left segment of the beam, shear does not exist at x equals 0 and x equals 2.5, where concentrated loads are present. The same principle applies to the other beam segments. For the middle segment, shear does not exist at x equals 2.5 and x equals 7.5, and shear is non-existent at x equals 7.5 and x equals 10 in the right segment of the beam. Now, let's examine the short beam in the front of the building. A 350 millimeter thick concrete slab rests partially on the beam, which is 6 meters in length. The width of the slab is 3 meters. Since the slab rests on the beam, half of the total weight of the slab is going to be placed on the beam as a distributed load. The intensity of the distributed load is 12.6 kilonewtons per meter. How did I arrive at this value? I multiplied the specific weight of concrete by the thickness of the slab, multiplied the result by 3 meters, the width of the slab, and divided it by 2, since half of the weight is going to be supported by the beam on the other side of the slab. Here is the beam subjected to the distributed load. To determine the support reactions, we are going to write and solve 3 static equilibrium equations. Knowing the reaction forces, we are now ready to write the shear and moment equations. Since there is no point of discontinuity in the applied load, we need only one equation for shear and one equation for bending moment for the entire beam. To write these equations, we cut the beam at an arbitrary point, like this. Let x represent the length of the segment from the left end of the beam to the cut point, so x could vary from 0 to 6. We use V and M to represent the shear and moment at the cut point, respectively. The 2 equilibrium equations for free body diagram are. Solving these equations for V and M gives us the shear and moment equations. Let's summarize what we know. We can describe shear and moment for the beam using these equations. Just like the previous case, the shear equation here does not cover the ends of the beam where the support reactions are located. The moment equation, however, is valid for the entire beam, including its endpoints. Now, let's turn our attention to the side beam. It's subjected to two loads: a concentrated load due to the weight of the staircase and a distributed load due to the weight of the concrete floor. The staircase distributes its load to the supporting beam, which in turn transfers half of the load to the side beam. In our case, we assume the share of the staircase load applied to the beam is 5 kilonewtons. The distributed load due to the weight of the concrete floor is assumed to be 8.4 kilonewtons per meter. The length of the beam is 8 meters, with the concentrated load being applied at its midpoint. Similar to the previous two cases, we start by determining the support reactions. Here is the free body diagram of the beam, and here are the resulting equilibrium equations. The support reactions for the beam are: here, the loads divide the beam into two segments. So we need two sets of shear and moment equations. To come up with the equations for the left half of the beam, we are going to cut the beam at an arbitrary point in the left segment. As usual, the shear and moment at the cut point are labeled V and M. The length of the segment is labeled X, which could take any value between 0 and 4. The resulting equilibrium equations are: solving these equations for V and M, we get the shear and moment equations for the left half of the beam. For the right half of the beam, we cut it at some distance x from the origin, where x could take any value between 4 and 8. This free body diagram results in the following equilibrium equations, which would give us these shear and moment equations. Here is the summary of the results. Now it's your turn. See if you can come up with shear and moment equations for these beams.
So try to find out the shear force and bending moment for these kind of beams. Okay. Write your roll number in the chat box. And you are left to write the roll number. I'll call out once, okay? Check. 74, 71, 81, 93, 82, 51, 70, 103, 63, 76, 119, 94, 83, 52, 88, 67, 109, 68, 62, 75, 78, 92, 61, 110, 12, 72. Anyone left? 84. Okay. Thank you. See you in the next class.